Hello and welcome to week 11, lecture 1 of CO 442642 graph theory. Today we'll be discussing more on Ramsey numbers. So to remind you what a Ramsey number is, the Ramsey number of a graph H, denoted RH, is the minimum integer n such that every two coloring of the edges of Kn contains a monochromatic copy of H. So as part of our discussion about finding structure in disorder. And more generally, we'll define the Ramsey number of graphs G and H, denoted RGH, as the minimum integer n such that every two coloring of the edges of Kn, and here we'll think of the colors as red and blue, that you either contain a red copy of G or a blue copy of H. So what if we wanted to break the symmetry and find G in the red edges and H in the blue edges? Then we'll have this RGH. And as cliques are kind of fundamental to Ramsey numbers, we'll define R of K to be R of KK and RKL to be RKK-KL. Alright, so then today we'll be discussing various bounds on the Ramsey numbers. So we saw before that they exist and gave some upper bound. Let's talk about the bounds for small numbers. So R of 2 is 2. Right, so if we color that edge, it either has to be red or blue, and you'll get a red K2 or a blue K2. R of 3 is 6, you might have seen that before. K5 decomposes into two 5 cycles, and so it doesn't have a triangle there for that edge coloring, but when you have K6, you actually do need either a red or blue triangle. It's known that R of 4 is equal to 18, so that was proven. Whereas R of 5 is actually still open to this day. It's known to be between 43 and 48, which may seem like a large gap. We haven't even narrowed it down to two numbers, but that's actually not so bad compared to, say, R of 6, where we know it's between 102 and 165. And from there, the gaps get even worse. So there's actually a rather famous quote of Paul Erdős, who said the following. Suppose aliens invade the Earth and threaten to obliterate it in a year's time unless human beings can find the Ramsey number for red 5 and blue 5. So if they could determine R of 5. We know it's down to 43 to 48. Then his suggestion was that we could marshal the world's best minds and fastest computers, and within a year we could probably calculate the value. However, then, so he's suggesting R5 isn't impossible if we used all of the world's resources, all of the computing power to do that. However, he said, if the aliens demanded the Ramsey number for red 6 and blue 6, or R of 6, however, we would have no choice but to launch a preemptive attack. That really it'd be very hard, very difficult. R6, our best bet would just be to defeat the aliens. And that's just R of 6. So going beyond that, R7, etc., would be very hard if you want to pin down the number exactly. It's possible to find a problem. You only just have to spit out all the graphs and check them, but there are just too many graphs on even vertices, like 45 vertices. So those are the bounds that are known for the small numbers, at least for the diagonal ones, for R of K. What about generally? Well, last time we saw an upper bound. You can actually do slightly better. There's a theorem of Erdős and Sekerish, which says that R of KL is at most R of K minus 1L plus R of KL minus 1. So this was the proof of this. It's the same as last time, it's just the majority argument. So you look at a vertex and you see whether it has more red neighbors or blue neighbors, and you'll realize then, that you'd have to have one of those, and then you could do induction. You could find that number. So what does that say? It seems you should remind you of something, this kind of expression, namely it seems similar to how binomial coefficients work. And indeed, if you understand what the base cases are, it's not too hard then to get as a corollary that R of KL is at most K plus L minus 2, choose K minus 1, or equivalently L minus 1, as they'll be symmetric. So that's a nice upper bound, and if you actually know the asymptotic formulas for the binomial coefficients, if you plug in for RK that L is equal to K, you can derive that this is at most on the order of 4 to the K minus 1 over square root of pi K. So you might know the binomial coefficient, of n choose n over 2 is approximately, 2 to the n but actually over even square root pi n. And so if you do that here, you'll get roughly those numbers. Okay, so that's the Ramsey bound, the upper bounds there. Actually, there have been improvements. So in the last, half century, Conlin showed in 2009 that you can actually not only get 4 to the k, but you can do a bit better than even 4 to the k over something like root k. You can get at most k minus c, c is some constant there, log k over log k times 4 to the k. So really you can beat any polynomial lower bound on the denominator there. And just recently this year saw prove that you could do improve that by getting rid of the log k. So k minus c to the log k times 4 to the k. And that's currently the best known upper bound generally on R of k. And you'll note there's still been really no change in the base of the exponent from 4, so we can kind of do 4 to the k over something super polynomial, but we don't even know 3.99 to the k. So that's the upper bounds. So we've improved a bit on this easy majority argument, but not enough to change the exponent. What about lower bounds? Well, Erdos rather famously in 1947, and we'll actually do the proof of this in a second, showed that you can get a lower bound of at least kind of k over root 2e, 2 to the k over 2. And the only improvement since then has been Spencer from 77, who improved this by a factor of 2. So proving that you get square root 2 k over e, 2 to the k over 2. And again, you'll note that there's been no change in the base of the exponent from here. It would be square root of 2. So it would be square root of 2 to the k. That would be what 2 to the k over 2 is. So we know that it's somewhere between square root of 2 to the k and 4 to the k, but we don't actually know what it is. The number exists, the limit actually exists, but we don't actually know about the base of the exponent. All right, so that's still no change in the base. What about Erdős's proof? So this is our first taste of kind of the probabilistic method as utilized by Erdős and now become very widespread in combinatorics. And in particular, we'll discuss random graphs. So a definition, if you haven't seen this before, GNP is the random graph on n vertices where every edge is present independently with probability p. So you think of a graph on n vertices, you mark every possible edge, and you flip a coin for each one with probability p, so a weighted coin there, and put the edge in that case. And this is, we think of this as a random graph as the outcome is a random variable. So there'll be different instances. You can also think of it kind of as just kind of a probability distribution with certain weights for certain graphs, but it's easier to think of it as this random process. And then what's the point? Well, we can use this random graph, we can prove properties of it with basic probability in an effort to show that actually there has to exist some graph without a large cliquer independent set on the right order for the Ramsey bound. So let's study this. So here's a lemma. The probability that GNP contains a kk is at most n choose k, p to the k choose 2. So you could stop and prove this. We'll do the proof. So if you haven't seen probability, it's not very hard. So you just think about the probability that a fixed set U of k vertices is a kk. So I think about a subset of k vertices, I would need all the edges to be present, so that would be exactly the product over the edges of the p's. As they're independent coin flips, it'd be p times p times p, etc. There are k choose 2 edges possible in our k vertices, so we get p to the k choose 2. And then the point is you can use something called the union bound, right? So if GNP was going to contain a kk, it'd have to be that some u of k vertices is the kk. So we can upper bound that by summing over all the probabilities that a fixed u is a kk. And then the question is simply how many choices there are for u. There are n choose k choices for a set of k vertices. And then the lemma follows. So this might be a bit sloppy, as there might be actually be able to do better and to have some interaction. Some of these will overlap, but we can just use this kind of a union bound to say worst case you get this, and that's an upper bound on the probability. And now the point is you could kind of see that if you choose n small, this probability will be quite low. So that would be a way to make sure the graph hopefully doesn't have a kk, But actually, similarly, the probability that G and P contains an induced KK, so an independent set of size K, is the same except that we're looking for non-edges. So those would happen with probability 1 minus P. So we get an upper bound of n choose K, 1 minus P to the K choose 2. And now all that remains is to choose n and P. So since, there's really symmetry between the KK and the complement of KK there, we'll choose P to be a half. And then if you let n be the number from the Erdős's theorem, k over root 2e 2 to the k over 2, minus a little bit, and you'll see what that should be in a second, then actually you can put this in and kind of find your graph. So how does that work? Well, you get that this number, if you put in either p or 1 minus p, either way it's a half. So you get this upper bound on the probability of n choose k half to the k choose 2 if you approximate the binomial coefficient with ne over k to the k, which is what it is asymptotically, and rewrite the half to the k choose 2 as 2 minus kk minus 1 over 2. And then you plug in the n. You'll notice that the e and k parts will cancel, and we'll just kind of have a 2 to the k over 2 over root 2, which becomes 2 to the k minus 1 over 2. And that will get raised to the power of k, and that will cancel out the 2 to the minus k minus 1 over 2. And you'll be left with this 1 minus O of 1 to the k. And so if we choose O of 1 to be small enough, something like or rather large enough, something like a 1 over k, you'll get this being like at most 1 over e, and that's at most a half. So this would show that, if we choose n correctly, the probability you contain a kk is at most a half, but the probability you contain an induced kk symmetric is also at most a half and strictly less. So if you union bound and sum the two, you find the probability of either is strictly less than 1. And what does that mean? It means that there has to be some chance, some probability that you actually have this not happening, that neither of those happens. But that means there's some graph on n vertices with no kk or induced kk complement there. And then that concludes the proof. That would be our coloring, again, coloring the edges and the non-edges, red and blue, of Kn. That would be our Ramsey graph there. So that's the idea. We used a probabilistic method, so we define a random graph as some kind of experiment, a random experiment for creating graphs, and we showed that with some positive probability, we don't have these bad events, these large cliques or independent sets, so we know it exists. But we don't actually know what the graph is, we just know that that it succeeds. And actually, if you look at this proof, we could make those probabilities low, so it actually succeeds actually a lot of the time, more than half the time, or 90% of the time, etc. So somehow, if you choose one on that number of vertices, you're kind of likely for it to work, but we don't actually have kind of constructions of what those should be. We just know by randomness they do exist. So that's our first taste of the probabilistic method and the proof of the Erdős lower bound. I wanted to do one last proof for today on the Ramsey numbers, which is about bounded degree graphs. So there was a nice theorem of Quattel, Rodel, Semeretti, and Schroeder in 1983 that gives a nice bound on the Ramsey number of graphs more generally, as for every delta at least 1, there is a constant c greater than 0, such that every graph h with delta of h at most delta satisfies that its Ramsey number is at most c times v of h. So this is quite a nice theorem. So even though for the main Ramsey numbers we don't have good bounds, if you want to think more generally and think about kind of graphs that have bounded degree, so you're kind of thinking the number of vertices is much, much larger than delta, this would provide a pretty good bound. That really, it's kind of linear in the number of vertices as long as you think of delta as bounded, so that constant only depending on delta. How would we prove this? Well, we'll resort to a lot of things. I'm just going to do a sketch today, and you can read the proof at Diestel. But the proof idea is to apply basically all the theorems we've learned over the last couple weeks, namely the regularity lemma, Taran's theorem, Ramsey's theorem, and the blow-up lemma all together. So really, it's a consequence of the regularity lemma, a proof from that, but which is also going to use Taran's and Ramsey's. So here's our proof sketch. You apply the regularity lemma with m large enough and epsilon small enough and obtain a regularity partition. So I could tell you what the m and the epsilon will be. Let me not do that and skip those details. That's really going to be the only part of the proof that's really missing. But you'll see that, we'd have to choose them appropriately, but if you think about it, we'll be able to do that. And that's rather typical for these kind of extremal proofs, is that there's parameters and somehow you reverse engineer what they should be after you've done the proof. Okay, so then what's the key idea is that we let R be the regularity graph whose edges are the epsilon regular pair. So forget about density for a moment and just think about the graph where you look at the regular pairs. And what you know is that there are most epsilon k squared irregular pairs, and epsilon is small enough. So what does that mean? That means by Taran's theorem, this graph is very dense. It's very close to having almost all the edges. So by Taran's, we can find a large clique. So we can find a subgraph of the regularity graph where all the pairs are regular. And how large can we find it? Well, it's going to be useful to take as the size of the clique the Ramsey number of delta plus 1. So that's the key. We'll take the Ramsey number of delta plus 1. That's what that R of delta plus 1 means, as delta plus 1's a number and R of that is its Ramsey number. And so why is that useful? Well, it's only at this point, remember we're trying to do Ramsey theory, where we're going to consider a two-coloring of the edges of this subgraph, the regularity graph H. Namely, we'll color a pair red if its density is at least a half. So, it's regular, it's random-like if it kind of has a good chance to have edges, so density at least a half, we'll color it red, and blue if the density, say, is smaller than a half. And then we'll have a red-blue coloring of the complete graph on R of delta plus 1 vertices. So what does that mean? That means that by Ramsey's theorem, there exists a monochromatic k delta plus 1 subgraph of H. Call it K. Right? So we knew from kind of Taran's that we can ignore the irregular pairs and actually find a clique on just regular pairs. And then we kind of this two-coloring red and blue of high-density, low-density pairs. By Ramsey, we can find a monochromatic subgraph. So now there are two cases. Either K is colored red or it's colored blue. So what does it mean if it's colored red? Well, that means that we have a clique of all of high density. And then that gives us that by the blow-up lemma, G contains a copy of H. So if you remember, we can embed H, and because it's a max degree delta subgraph, we have the parts, delta plus 1 parts, to do that, to go back and forth. And that really only depends on delta. So we only need that the size of the parts actually have a number of vertices on the order of V of H, which we'll have by our assumptions. But otherwise, these parameters, the epsilon, the number of starting parts m, really only have to depend on delta, because we only need that for the blow-up lemma. And we also need, like the number of parts to be at least the Ramsey number of delta plus 1. But again, that only depends on delta. And similarly, in case 2, if it's colored blue, that would mean that the subgraph there has all low-density pairs. So you might have some edges, but kind of they're low density. And what that means is if you apply the blow-up lemma to the complement of G, then it actually contains a copy of H. So we can go past to the complement and find the copy of H as a blow-up, that we can find the non-edges as they would for H. And that, again, works the same. So that's the proof sketch of this nice Ramsey bounded degree. We used Taran to find a clique with all regular pairs. We used Ramsey to either find a clique on high-density pairs or low-density regular pairs. And then we apply the blow-up lemma either to the graph or to the complement to get the copy of H. And again, you just have to make sure the number of parts is enough to apply Taran's and Ramsey's, and that epsilon works to apply Taran's and the blow-up lemma and such. But you can work out those details. Again, read the proof in D-Stool. But it's quite nice as a culmination of a lot of the theorems we've seen so far in this class. So that was our talk about the Ramsey numbers. We've gotten exposed to the probabilistic method. We'll pick up next class where we'll dive a little bit more into the probabilistic method and how to apply it to prove some other theorems. So until next time, see you then!